The proof we'll be looking at is example 4 in the PowerPoint slide, and it is found on page 81 as result 3.4 in the textbook. And the textbook is this one here, Mathematical Proofs, A Transition to Advanced Mathematics, 3rd edition. How to do this thing here too. Okay, so if you have, so let's first think about what odd and even integers are, unfortunately. So if we assume that n is even, how can we represent an even number? This, if n is even, we can say that n equals this thing here, this expression. This is an expression for even numbers. If n is, let's say, 4 is an even number. Now my job is to find a k that if I multiply 2 into that k, I'll get 4. That's 4, that's even. Let's say 8. That's too easy. Let's do something really complicated, like 0. 0 is an honorary member of the even class. So, k, is there a k? Does a k exist in the world if I multiply 2 into that will get me this even number? And the answer is 0 itself in this case. Let's do just one more. Let's do 6. And in this case, up here we had a 2, which was even. In this case, is there a k? If there exists a k that if I multiply 2 into that k will give me an even number called 6. And what is that? 3. Somebody said 3. I'll repeat. And bam, we have 6. And it is an even integer, for instance. In mathematics, this is called a statement. And if this statement is true, statement is something that can be true or false. In this statement, we have an expression. It's a very simple mathematical expression. It's just one variable, m. It's just like our x right now. If we assume this to be true, if you come in here, if we assume this to be true, then we can rewrite this statement as I'm just saying, because what this is saying n is an even integer. This is saying n equals an even integer. Because this is definitely always an even integer. Put any k in there, odd or even, multiply 2 and you're going to get even. So this statement itself, this is another way to restate that, if we assume this is true. Okay. All right. Now let's look at odd integers. So if this is how we represent even integers in mathematics, so for odd, let's say we assume n is odd. So how do we express odd integers? Well, if you give me an even integer, I'll just add 1 to it, and I'll get an odd. 2 add plus 1, 3. 5 is odd, plus 1, 6. So right now n is even, now it's odd. So to express odd integers in mathematics, this is our friend here, right there. This part here. Okay, so textbook authors are going, we need to teach students how to do direct proofs. Let's make up an example and then we'll show the steps for that direct proof. And in that example, they came up with this expression here. This is an expression because there's no equal to sign in something. Then it's an equation. So this is a mathematical expression. So they came up with this expression. They said, okay, let's say something really cool about it. And they came up with this expression sums up to a even integer, always. If and only if we stick an odd number in there. So this expression, if you stick in an odd number here, will always give you an even integer. Okay, so we could run through a couple examples and see it will always be even. So it's kind of like in some sense it's like the 2k thing. So if I add, let's put an odd number here. I put 3, 9, and yeah, that's 14. If I put 1, which is also an even number, odd number, and then I'm going to get 10. Right? These both are even. I could keep doing this for 2 centuries. Is it? I think 6. Yeah. Thank you. That's messed up. Thank you. Somebody saved me in the class. This will not be deleted. Okay, let's do one more. No, we don't need to do one. I could stand here, keep doing this, and every time I'll get it. Is that a proof? It isn't. We haven't definitely proven that if n is replaced by an odd integer, this thing sums to an even number. But to right there. So our expression is 3n plus 7. It is an even integer. You see the font size is quite big. If the n that we replace, so n is going to go here, is an odd integer. If n is an odd integer, then this expression will always sum to an even integer. And so I put an int here. So now what you have is an implication. And so somebody was playing around with that, thought of what if this was odd? Will it always give me even integer? It's like, oh yeah, it does. And then, so this is the result that we want to prove. This is the statement 1, this is statement 2, and this is the implication part. So this is called a statement, or another word for this is the antecedent. And that part is called the consequent. Or this is a statement. Yeah, you can still read it. Can you see it on the diagram? We could call this statement P, and we could call this statement Q. So if P is true, then Q is true as well, or something like that is going on there. Or that P implies Q, or the antecedent implies Q. So in logic, we would say it like this. We would say, this is the symbol for implication. And then since we are dealing with variables, we can do this. There's a P condition and a Q condition. This is what we're going to do using direct proof. So we still haven't got there yet. All right, so let's start doing that. So what's the first step in a direct proof? So I'm going to write, so our proof is going to start right here. And I'll be out here. Direct proof. And of course, Okay, so step one is the assumption step. You have to assume the antecedent to be true. In other words, the n that we will replace here will be a odd integer. So we assume that to be true, and when we assume that about the antecedent or the statement P to be true, we can then reformulate n and express it as a odd integer. Okay, so let's do that. So from our step one, so the first step of a direct proof is to assume the P or the antecedent to be true, and then we get something that we can then plug into this to show that this is always even. So our assumption about this statement gets us this, that n can be represented as and now the second step two is to go ahead. Step two is to use what we found in step one let's use what we found in step one and start here. So so we did the first step, and that got us, we need more spaces at the time. We got this. And now we're on the second step. So we write this expression. And I'm going to do it in one straight line here. We want this expression to look like the expression for even integers. We want to move things around here so that by the end we have a 2 in the front and then whatever after that. That whatever. Okay, something like that, that 2k thing. Because 2k are even numbers, 2k plus 1 are odd integers. All right, so 3m. So what's the first step? By assuming this to be true, that is, this is always an odd integer, we can replace n with this formula right here. So we got 3, and this goes in here, 2k plus 1 plus 7. This is, and this is when algebra comes in and I get stuck. So we just distribute 3 over. 3 goes here, 3 goes here. So now we have 6k plus 3 plus 7. Looks okay. Okay, so I was going to go straight, but we're going down. Now, does this thing look like we've got a 6k plus 3 plus 7? So this is our expression. We want to take it to where it starts to look like that. So we definitely need a 2 out. And when I look at 6, it's an even number. There's a 2 in there. If we add these two guys up, there's a 2 in there because that becomes 10. So we do that. Let's see, 6k plus 10. Oh. And I'm going to take it over there now. See a beautiful 2 coming out. This is 3k. 5. So in some sense, this is our k here, this whole thing. We got a 2 out. Whatever k is, it doesn't matter, it's odd or even. Whatever k we stick in, because we are multiplying it with 2, this whole thing will become an even integer, always. Therefore, what we've shown is that if you stick in an odd integer here, this will always sum up to an even integer.
Can you get any even integer?
Yes, it will be random.
Or
Like every integer. Yeah.
You good?
Don't know. I don't think so because this seems pretty specific.
When you're done there, if that's it.
Yeah, then that's the proof.
Yeah.
And to end the proof, you have to put a square box there. But that's a very good question. I don't think so. Every and all integers, even integers, formula for that is this. If you want to generate every odd integers, that's the formula right there. And you can also, k can be negative, then you can get negative odd integers and all of that.